Robin Post van der Burg from Green and Gas from the Netherlands. He's the general manager of this company. He has more than 10 years experience in chemical industry in the Netherlands, UK, and in 2012 he co-founded the Gas. And this is also what he will talk about today. The feedstock flexible routes for biomass to chemicals and fuels. So, the floor is yours.
I want to thank on this one. Thank you so much for the introduction. So I think I can make a statement that climate change is the hardest joint project humanity has ever faced. And the thing is that we all agree on that, but we do not agree on the technical solutions we have out there. And the cognitive dissonance between hope and despair is enough to make everybody's mind spin. So I'm going to tell you now a story about what we believe is a integrated value chain that could really be the future of our biomass to chemicals and fuels. And then you come to three essential criteria if you're going to make these molecules, and that it's scalable, and I mean scalable both from the feedstock side as well as from the technology side. It should be affordable. I think it's very dangerous to come with solutions that might work in our very wealthy northwestern world, but it should be available to everybody, and therefore it should be affordable. And it should be sustainable, and even preferably carbon negative. So, the transition. If you look at the current fossil feedstock usage, you see that only 25%, more or less, I got this number from the EAA, is relating to the production of electricity. However, 75% relates to all the other conversions of fossil fuels. So we're talking about LPG, kerosene, bunker fuels, and chemicals, and much more. So chemicals, fuels, materials. And we need a sustainable solution for that. So actually, what you see a lot on conferences, that everybody talks about the energy transition, but actually we're dealing here with a completely other transition, which is the feedstock transition. Now my slides doesn't go to the next one. And this feedstock transition requires a lot of carbon and hydrogen. And I hear a lot about hydrogen. I think there's maybe a hype even about hydrogen. But a lot of you are chemical engineers or are chemists, and we all know that all these molecules are mainly carbon. So we need this green, sustainable carbon. And it has to come from a sustainable source, not from a fossil source. And again, it has to be sustainable, scalable, and affordable. So then we start to think, how many options do we actually have? Well, first we have the fossil route, which is obviously affordable. It's very scalable, but it's not sustainable. So we have to stop it. We have to keep on doing it, but we have to work as hard as we can on solutions. Then we have the E route. We actually had the first electrolyzer permit in the Netherlands in 2014, just to give you an idea. We were already looking at it because we could use hydrogen as an add-on in our gasification to plus our hydrogen, and we could use the oxygen in oxygen-low gasification. So we started to look at it, and we did some math, and we saw it was sustainable. But then we saw it's not scalable. And some people claim it's scalable, but think about the amount of rare metals that will be in this electrolyzer. So you have to really think very carefully here. And what we really found out, it was not affordable. It was so expensive that we thought, why does it get so much attention if it's not affordable? And then you have the bio route. And they have a route that is affordable, scalable, and sustainable. And I'm going to also make very clear why this is. So, for instance, let's look at crop residues, because one of the arguments we always hear in biomass is that food versus energy, which is actually completely the opposite. It's actually food in synergy with energy. And if you look at our main food crops, only roughly 20% is the food we're eating. So that are the starches, the oils, the fats that goes into our food chain. And about 20% remains in the soil. But this other 60% is actually residue, which is in a lot of countries set on fire. So can you imagine? Each year we are throwing away a lot of carbohydrates by just burning them in the fields with very harmful impact on the local environment. Not so much in Northwest Europe, but already the straws in Eastern Europe and in other places nearby are already put on fire. And then the number. A lot of people are saying there's not enough biomass. I hear it all the time. Now there is a lot of biomass. And they're saying like, hey, there's not enough sardines because we only have 2 rods to fish for the sardines, so you don't catch a lot of sardines. But it comes with a completely different approach. So the EAA published a report 2 years ago that crop residues on this planet amount for over 5 billion tons dry bone. 5 billion dry bone tons. So that's a phenomenal amount. And I'm not talking even here about other residues like invasive bush, like in Namibia or Southern Africa, but you see it all over the place. In Eastern Europe, they have harvest about 3 tons of acacia per hectare per year, which has to be taken out. Invasive bush is one of the most problematic threats to our nature systems or their habitats. And we also have a lot of other residues we can talk about, demolition wood, residual chips. But food crops I'm going to talk about. So 5 billion tons is a lot. If you take, for example, the total global consumption of kerosene, it was last year 20 billion gallons. That's about 75 million tons, or 65 million tons. You need about 5.5 tons of dry bone biomass to produce a ton of SAF. We believe that one of the most interesting routes is over a methanol platform. So methanol, due to the high selectivity, and then from methanol to kerosene. And you need also some aromatics, but the key component will be over the methanol route. Second one is methanol. As mentioned, methanol is a pure form for shipping. You have seen the announcement maybe of Maersk. Maersk is betting on methanol. As the sustainable fuel of the future for their shipping. Why? Because it's a much less dangerous product than ammonia, and it has a lot of other advantages over ammonia in shipping, which was also pushed through the chain. And then we're talking about roughly 220 million tons of this crop residue. So to substitute all SAF of all kerosene and all methanol currently produced, I'm not talking about the growth in shipping, but currently produced, we need about 10% of the crop residue to be unlocked, to use that as a fuel for feed. I'm not again talking about the other potential on this planet in feedstock. So it asks for a completely different approach. This is all about the unlocking of the carbon at the source. So technologies that convert the biomass in a usable commodity form. Then you get crop residues. Then I'm sitting a lot with politicians, and then I hear, oh, it's so supported. Oh, it rots. Yeah, correct, it rots, and it emits a lot of methane and CO2 into the atmosphere. So if you can use it, it's a double-edged sword. And you have the methane emissions. So you have to find a solution from the rural areas. Fossil fuels come at point sources. This material comes spread out all over the planet, where you first densify the material, and then you may make a way for this bulky transport to concentrate the biomass and to bring it to the industry. So the key word here is torrefaction. Torrefaction is a very selective process that removes at a certain temperature range the hemicelluloses from the biomass. And the hemicellulose is like the glue in the biomass, so it makes it brittle, and it makes it a much better grindable product. So the crop residues goes in. You treat it about 250 to 280 degrees. Be careful, if you go higher, you're coming into an exothermic zone where you also start to have runaway reactions of the cracking of the cellulose, and you want to avoid that. And then as a product, you get a torquette. And you get an energy densification from the raw material to the pellets of a factor 7-8 for wood residues to even up to 40, for example, for bagasse, which is enormous. So 40 trucks with bagasse arriving, 1 truck going out, and retaining about 85 to 90% of the lower heating value. So then you have solved one problem once you've done that at a scale. And that's that you have the fuel available. Because if you don't have the fuel, if you don't have the feedstock, you cannot feed your processes. And then you take a lot of the concerns by politicians, by decision makers away, because it becomes hydrophobic instead of hydrophilic. It becomes inert, because you can keep them for years, you can store it. It's actually the storage of solar energy. You stop the emissions, the harmful emissions from the rotting biomass. And you have also a commodity that can be transported with almost a similar density as biomethanol, about 16, 17 gigajoules per cubic meter. It's not fibrous anymore, it's friable, and it becomes homogeneous. One of the key elements, gasifiers that have to run every day on different feedstocks with different composition, with different moisture content, with different sizing, they have a huge problem in the future, because you cannot do that on an industrial scale if you want to change the whole industry. Then we come to the next step. So we decouple the feedstock preparation from the place where you gasify. Then you come to our second technology. And then we're talking about gasification. I have to give a big thank you here to Fraunhofer Institute, who really were essential in the whole development. Is that you have to deal, first of all, again, with the feedstock stability. The second well-known dilemma in gasification is slagging, especially in biomass gasification. I don't want to sound as a warning, but if you apply for biomass and train flow gasification, high temperature, you're destructing the minerals. And sooner or later, the NGOs will get on your back because they won't accept that the minerals coming from the soils will be destroyed. You can do that for waste, but for biomass, it's a non-circular solution. Maybe for the carbon, but not for the minerals. So that's really important. And the third one is star formation. And as most of you know here, or everybody probably knows, they go counter-effective. So when you have a low temperature, you have a lot of tar, and if you have a high temperature, you have a lot of slagging. So you have to make a choice here. So we solved the stability issue by applying torrefied material, where we can scale it really up because we're not dependent on the local supply. And you get into our two-step gasification process. So stable feedstock, and then we have a low temperature gasification. We just heard about the Coran. Now this is actually the former Coran low temperature gasifier, but that was fed with wood chips, so it didn't produce what we do with char, because we have a moisture-free feedstock going in, and we produce a char, which is a very interesting product, because again, it's the most wanted voluntary credit on the planet right now is biochar. You can put it back into the soils, but you can also convert it, for example, into graphite, so you can make biographite. So it's a very interesting product, obviously depending on the feedstock, what quality you're going to produce. And in the second stage, it makes it carbon negative. So it's really important. The interesting thing is we're not only making syngas, we're also producing the biochar that is stored for long, and it's a way of carbon sequencing, which is really important. And we have been assessed with the whole value chain as carbon negative. The slagging has been avoided because we concentrate the minerals in the biochar. Again, all oxygen blown, steam blown steps. And into the second step, we go to very high temperature where we crack the producer gas, where it's also the BTXs in there, and we crack them to a pure syngas. Obviously with some CO2 in it, because we have to go to temperatures like 1200 degrees. But we crack the tars. And this has all been proven at the TRL 711 at the DNV Gasification in Groningen. And then we get a biosyngas. And the CO2 can be separated, can be liquefied, and sold as a product to substitute the fossil CO2, liquefied CO2, which is coming from steam reformers right now in ammonia production and methanol production. And then we have a chain that you can go to DME, you can go to SAF, methanol, and olefins. And whether it's olefins and a methanol to olefins platform, or a Fischer-Tropsch platform where you do the Fischer-Tropsch condensables into a naphtha cracker, that's not to us. We are producing the syngas, and then the industry can decide. But they have a drop-in solution, for example, in this case, towards olefins. And as we all know, olefins is 80% of all plastics and roughly about 60% of all chemistry. Again, we are big fans of methanol for the reason that we believe methanol will be a pivotal molecule of the future because it serves the chemical industry and it serves a lot of the fuel industries. It was mentioned before, methanol to gasoline, methanol to kerosene, and methanol as a standalone fuel. And obviously DME is also actually a derivative, but can also be directly made from syngas. So we have here a complete supply chain solution, which is avoiding that crop residues will be combusted in the plantations. The torrefaction, we have the mobile torrefaction system, and I will show a video how it works. It's at TRL7 right now, and we're ready in the next years to roll it out around the world. It densifies the biomass. It is very tolerant towards a lot of biomasses, but it can deal with the seasonality issues and the transport issues. Then we have the two-stage tar gas process where we avoid slagging, we avoid tar formation, and we have a stable feedstock. The biochar, again, I hear a lot of, especially the fossil conservators, we want to have the maximum amount of gas. Yes, they might have, but we want to have the maximum sustainability, and this is the maximum sustainability. And sooner or later they find out that this is the only right way to go. And then we have the biosyn gas, and we can make the molecules. So it's sustainable, it's scalable, and it's affordable. I didn't spend a slide on affordability because I don't want to give everything here to the table. But typically of the 3 projects we have in the pipeline, the levelized cost of the syngas is anywhere from 50 to 70 euros a megawatt. And then we're only at the beginning with very high infrastructure costs. And you can imagine that it's all about this infrastructure. Once the capital is depreciated, the syngas gets very competitive with fossil. So I'd like to thank you for your attention. If I'm allowed, Professor Greger, I'd like to show a video with the questions. Then it would be, and I have to start this one, and I have to need some help how I do that. Because it really gives you a 3-minute.
I don't know. You keep the people from eating, but...
Oh, sorry, if you want to go eat, please go. I'm not insulted.
In our concern for global climate change, biomass is a determining factor. It is remarkable that it is not at the forefront of our minds, while it can make the difference we're looking for. In fact, with biomass, we could turn a problem into a solution. Because crops such as wheat, sugarcane, rice and corn produce large quantities of residues. Only a small part of the corn plant, 20%, is corn. 80% is residue. The worldwide quantity of these residues is enormous. The global production of corn alone produces over 1 billion tons of byproduct annually. If we could only put this to use, we could deliver biofuel for all of the world's heavily polluting ships and aeroplanes. And that's only considering the corn waste of all our crops. Biomass takes up a major part of the world's landscapes. At present, many feedstock owners have no use for their residues. So most of it is burned directly in the fields, creating pollution and fine particle emissions that affect millions of people. The way we treat bioresidues in large parts of the world has little value and causes a great deal of harm. There is a solution to this, one that is actually very effective and advantageous to nature, farmers, local populations and our planet. By processing and densifying the residues at the place of harvesting and turning them into a powerful substance. Since 2011, the TorGreen team has worked on the world's first mobile system for agricultural residues. Their solution for the residues problem is called torrefaction. This is a technique to compress biomass without burning it. This is the innovation. A mobile torrefaction unit converts residual feedstock into these torrefied briquettes called torquettes. There is 30 times more energy stored in these high-density torquettes, enabling very efficient transportation. From the biomass residue torquettes, we can produce green chemicals, biofuels, and renewable power. Things the world needs urgently and in large amounts. To produce green chemicals and biofuels, the tourquettes are the basis for a two-step gasification process, resulting in two main products, clean syngas and biochar. Syngas is so pure that it's the basis for a wide spectrum of chemicals. The most prominent is biomethanol, a chemical that can be processed into many products that are presently derived from fossil fuels. Biomethanol can be directly used as a fuel in conventional engines, and it's regarded as the game-changer fuel for supertankers on their way to sustainability. Biomethanol is pivotal in green chemistry, where it is converted into ethylene, propylene and butylene, and to produce bioplastics. Similar processes can also be used to produce biokerosene, enabling sustainable aviation. Prices of biomethanol are already competitive with fossil fuel prices, and they are expected to outprice fossil fuels within 5 to 10 years. Biochar, the second product to come out of this gasification process from biomass, is a high-value product, a stable form of carbon that improves the fertility of soils. It can also be applied in numerous products, such as composites, and as active carbon in highly needed water purification. If we torrefy biomass residues at the source, not only do we widely reduce CO2 emissions, but these agricultural communities also gain an attractive, clean business model, creating value for communities and the planet.